Yep. Yeah? Okay, you wrote this down?
Yes.
Right. Okay, so imagine a capacitor is fully charged up like in a camera, and then it's suddenly allowed to discharge, again like in a camera. So you press the button, the capacitor charges up, and then the flash comes out and it discharges through a resistor. In this case, the resistor is the bulb. So I'll just draw that again. So we imagine we have a capacitor and we have a resistor, and here the resistor is the flash bulb. But this time, let's imagine that we measure something like the current here. So tell me what you think happens. It charges up, and then I press the button and the flash is released. What type of graph do you think I might get for the current if I put time here and current here? So this charges up, has a charge, and then all the current comes out. What type of graph might I get? Yeah, but what shape? Up, down, constant?
No, it's like a triangle, like this would be a triangle.
So I should start high or low?
High.
Start high and then what?
Go low.
Go down.
Yeah.
Like,
Yeah.
and it go down straight?
I
You
think so.
think like this, yeah. Not bad, not bad. You have the right idea. In fact, it's more sudden than this. The graph will curve down. But you all have the right idea. Now, this type of circuit is a common circuit. It's called an OR-C circuit. The OR for the resistor and the C for the capacitor. That's why we call it OR-C. So the OR is for resistor and the C is for one capacitor. Right. I've already done that. So here is my example of some data when the capacitor is discharging through the resistor. And actually I should check some vocabulary here. So you remember charging?
Yeah.
The Q is increasing, and then the opposite of charging is discharging. The energy is coming out. You look confused. Yes, confused?
Charging and discharging.
So here, look, when I have it like this,
Yeah.
it's charging. And then when it's like this, yep, it's discharging. Yep. Is that okay? Are you sure? Right. So, here, it's discharging through the resistor. And can you see how the current is decreasing as the time is increasing? Yep. I'd like you to write this table down in your notebook as an example of some data here for this. Oh, and also I would like you to draw the OR-C circuit here like this. Well, yeah. So we have one capacitor and then one resistor. Yeah, you can draw it like that, yeah. So one capacitor and then one resistor. Could be a light bulb, yeah. Okay, you have this data? Watch what you're saying over there, Stephen. Alright, you have this? Okay. Continue. Mahmood, you still have lots of the table to write. No, I need to continue. Everybody else here has it. Yeah. Right. So what I'm going to do is I'm going to make the graph of this. So here we have time in seconds, and it's 0 to 10, is it?
Yeah.
Yeah. 0 to 10, wasn't it?
Yeah.
And we start current in milliamps, wasn't it? Starts at 100?
Yeah.
And what's the next one? 70.7. Like this?
No.
And,
Yeah.
and the next one is 50?
Yeah.
Okay. And so on, like so.
10.
10?
Time. The time.
Oh, thank you. To 10. Roughly, is it? Close enough. Okay, I need 2 decimal places then. Yeah, close enough. Okay, so let's have a look at the graph here. Scatter plot again. This one. So, discharging through a resistor. And the x-axis is time in seconds, and the y-axis is current in milliamps. So it's not quite a straight line, it's this curved shape like this. And you have seen this graph in maths class, haven't you? I think you have. Do you remember the graphs of this?
Yeah.
What do you mean, ha? You know this graph? Have you done this in maths? Anyways, if the A is positive and the B is negative, the graph will have this shape to it. If you didn't know it, that's okay, you know it now. So what I'm saying here is, as you can see, the graph is exponentially decreasing, which is not a surprise. So what we say is, the graph, the formula for the current, it looked something like this. The current will equal some current at the beginning multiplied by E minus time divided by some constant. This will make a graph like we have in the picture. Why do I feel like people haven't seen this in math class? Yeah.
And then we find the value of k.
Yeah.
No, T, not K.
X. So what? Yeah. You found the value of k.
Yeah.
You have done it.
We put the ln and then.
Yes, all of this stuff. Yes. So you have done it then. Okay. Have you got your maths there? Or is this just physics? Yeah. But have you done the graphs though? You've done graphs? Yeah. Like this one. Yeah. So you have done it. Right.
What is the
Oh yeah, I'll explain this now. So, this formula, it'll make a graph that looks like this. A curve shape. Yeah?
Like the U.
Like the U.
But it never touched.
But it never touches. Yeah. I know my graph is terrible. Yeah. It never touches here. Yeah.
So mine was
Now, we don't really want graphs like this in physics. We much prefer when our graph is a straight line. So the way we can deal with that is by using log. So watch what happens now if I use not I, but instead if I plot log of I. Oh my goodness, no, hang on a minute. Can I just move this to here? Is this okay? Yeah. So what I'm going to do is instead of using I, I'm going to use log of I. So all of these numbers, I calculate the log of them. Oh rats. Here, I'll type them in one by one. The first one is log of 100. The second one is log of 70.7, is it? The next one is log of 50. Next one is
35.4.
log of 35.4. Next,
25.
25.
17.7.
17.7.
12.5.
12.5.
Yeah.
Oh my goodness. Log of 12.5. Next, log of
8.84.
8.84. Next,
6.25.
6.25.
4.42.
4.42.
And then 3.13.
No. No, if I instead plot log I instead of I on my graph, so if I calculate the log of the current and instead plot that, what's happened to my graph now? This straight line, isn't it? And I need to change that. That should be log I instead of I.
How to change it?
Yeah, I'm trying to change it.
We just
I can't. In my graph, I should write log I, not I. So, why does log make it a straight line? Well, watch what happens. If I put log here and here, on the left I get log I. Oh, now, before I start, I have to give you a warning. Warning, I said there's 3 proofs you need to know for this course. The first one is UVATS, and the second one is what I'm about to do. Okay, so this is a proof you need to know. All finished? You're just here to cause trouble. How are your Greek letters?
Pretty good.
What's this one?
That one?
Yeah,
Over there?
this one. What Greek letter is this?
It's on
I know this one.
Do you?
Alpha.
Is it alpha?
New or something.
Beta.
Alpha, beta, gamma. Keep going.
Delta.
No,
Epsilon.
no,
Gamma.
no.
Pi.
Ask Stephen, you know pi is this one.
That's pi.
It's new.
It's not mu, mu is this one. Tau.
How?
Yeah, tau.
Oh.
What's the name again?
Yeah.
Guys, look, I'm nearly 40. I've made it this far without this far.
Yes, okay, yeah. Well, now you've got a new Greek letter if you learned. Tau.
Got it.
Got it. Alright. Okay, so you need this proof in the exam. So what we do first is we put log on both sides. On the left I have log I, but what happens on the right?
Link.
Log E equals
No.
log
What happens on the right?
The T over.
The from the exponential, this will come down.
E. Log
Nope.
I-O multiply.
Not multiply. No.
Divide.
It will come
No,
down.
not divide. Plus.
Oh yeah.
Why plus?
Log.
Because it's multiplying.
Because here
And
is
if it is
multiplying.
dividing, it will be minus.
Yeah. Now, what happens here?
T upon tau will come down.
Yeah, they cancel effectively. So you have log I equals log I0 minus T over tau. So log I equals minus 1 over tau T plus log I0. Now, what am I putting on my x-axis? T. And what will I put on my y-axis for my new graph?
No.
Log I. Yeah. So, the T is like the x, and the log I is like the y. So this is like y, and this is like x. So what type of graph is this graph? It's a linear graph. Yeah, it's basically a y equals a constant x plus a constant. So, when we plot the log of I, this is y, it's a straight line. And also, the m, is it positive or negative? Here. This is negative. So, is the graph going up or going down?
No.
Going down, which is exactly what happened here. Okay, this proof, all of this page, is something you need for the exam. Now, how will they ask you this in the exam? Well, they might say, can I scroll down?
Yeah.
Zoom out. They could say, prove or show or make this into a linear. Linear is the noun. What's the verb to make something linear? This is a noun, isn't it? So if I want to make a verb out of this noun, what would the verb be? Line it. I like it, but no. I do like it. Line it, but no.
Straight.
Straight it? No.
Okay.
But it's based off of this word.
Yeah.
So you're trying to make this a verb.
Linear.
What?
Linear. At last itself.
Oh, linear outlet. Nice try, but no. Linearize it. Have you seen verbs with a I-Z-E at the end?
Apologize.
Apologize, minimize, summarize. Yeah. It's summary and summarize. Yeah. Yes? Yeah, okay. Right. So, can I continue, Iyad? Well, it's you copy check. Okay. So I've already taken the log. So I've done this already. I've made the log of the I. And then when I plot it, what graph did I get? A straight line. Yeah, linear graph. And you notice how it's linear now. You do. Okay. Now, what happens when I put log on both sides? Well, this is here, look, linearizing it. So when you use log, you get this formula. And so, the y is log I. What's the m? Minus 1 over tau. The t is the x. The m is minus 1 over tau. And what's the c?
Log I naught.
Log I 0. And c is like log I 0. Okay. So if you can just make note of this if you don't have it. Yeah, that's fine if you haven't made note of it, yeah. Basically, this is the end of the proof.
Yeah.
Yeah. Okay, can I continue? I think you have this already in your proof. So, what's really nice is that this formula, it's the same for the current and the voltage. So the current exponentially decreases, and so we have this formula, we've just done that. But what's great is it's exactly the same formula for the voltage if you use a voltmeter, or the charge as well, that the Q equals Q0, and so again log Q equals exactly the same thing. True for the V as well. The V equals V0, E minus T over tau, and so what do you think the formula is? Log V will equal the same thing, yeah. So this is nice. It's really one formula for both I, Q and V. This is great. Now, I haven't actually talked about this tau. As we learned from Stephen Bruce, it's a Greek letter, and it's called tau. It's a Greek letter, and its name in physics is called the time constant. Now, wait one sec. Remember I said m equals minus 1 over the time constant? We can rearrange, remember the formula?
Okay.
So we can rearrange this as the time constant equals minus 1 over m, or 1 over the gradient. So we can have this formula for it. Yeah.
But why m equal 1 over 5?
Why? Oh, you break my heart. Breaking my heart. Here. This is like the m. Yes, thank you. It's okay, I feel better now. Right. Okay, so that's okay? Yeah? That's one formula to calculate the time constant. It's minus 1 over the slope. But what's the problem with this formula? Well, the problem is you're going to have to make the graph. Yeah, it depends on the graph, but the problem is you need to make a graph. So is there another formula to calculate the time constant? And there is. And the other way to calculate the time constant, and I won't do the proof of this, it's not on the exam, and I guess it's quite difficult. Another way to calculate the time constant is you take the resistance and you multiply it by the capacitance. So, which one do you use? Well, it depends. If you have the graph, you could use this. If you knew the resistance and the capacitance, you could use this one. So it depends on the situation. Now, what's useful about the time constant is that the time constant tells you how long until there's no current left. So for example, here is my graph. Let's do voltage, and here is the time. So it will decrease like this. Now I know you said it will never touch the x-axis. It just gets closer and closer. Yes? But at some point it's so close we can pretend it touches. No, don't be shocked. Don't be shocked, okay? So at some point we pretend it touches. And now it stops. it's reached zero. We use our imagination, we pretend. So the point that happens, the time when that happens, is going to be 5 multiplied by the time constant. This is the rule. Now I know it will not be 0, but this is what we use in physics. So we say the time to fully discharge is roughly 5 time constants. So no surprise for guessing what the unit is for time constant. What do you think the unit is for this time constant? Seconds. Yeah. That might seem a bit strange. What do we measure resistance in? Ohms. And capacitance? Farads. And it turns out ohms multiplied by farads is actually seconds. And I think you would like to see the proof of that. I think you would, wouldn't you? You would.
Yeah.
Look at you. You all want to. I know it. So look, yes you do. Time constant equals R over C. But what's the formula for C? Q over B. Yeah, and if we think about the VIR, what could we say for OR? V over I. Yeah? And then remember we have the formula for Q equals IT. Did we do that formula? Yeah, we did. We did do that formula. Yeah, we did. So here the V's cancel. Hold on, just relax. The V's cancel. And what's the Q? IT. And what happens here? The I's cancel, so you're left with a T. So
another formula and delete that T too.
So the unit for the T is seconds. So in other words, one, what do we say this was? Ohm. And this one, capacitance farad. That's the same as 1 second. Yeah. You don't need this one, it's okay.
What was Q equals IT?
We did this one in
I is equals to Q upon T.
I think the formula might have been written as I equals Q over
For
T.
the current.
The current is charge per time.
Oh,
Yeah. Right. Now I said here, no surprise the units are seconds, but maybe it is a surprise. Yeah, maybe it is a surprise. Okay. Right, I've got one example and then one homework question to do. So,
Both will do it.
We have time for the...
yeah, I mean, this one, I'm only going to use my Excel program, so I just need to... No way, I'm thinking. Do you know what? I won't do it, but wait.
I will get my pen.
No, you don't need to write anything. Just sit.
No, I will get it before I come back.
Right. So, Mir, stop moving and listening. Are you listening?
Yeah.
Right. So I don't have time to do this one, but it's not mad difficult. I'll just explain, walk through it, okay? So the first one is graph this. So what do we put on the x-axis? Time. And on the y-axis? We don't. We put the log of the current. Now, that's a typo. That should say what letter? Not A. It's I. Yeah. So we have log I and then time. So what's the first thing you need to do for this? Yes? What?
Convert down there.
Yeah, convert which one? This one? Yeah, linearize it. Change all of these into log their value. So this would be log 1000, log 841, log 707. Okay, good. Then what do? You make the graph. Now, because you have the graph, which you have the slope, and because you have the slope, you can get the time constant. Great. If you know the time constant, how long until it fully discharges? 5 of this answer. And then finally, what is the value of the resistor? Now, you know what the time constant is, don't you?
Yeah.
And what's the other formula for time
RC.
constant? Or C. Do you know the time constant?
Yeah.
Yes. Do you know the C?
Oh,
Yeah.
200 milli.
Yeah. So can you know the resistor?
Yeah.
Yeah. So I think this is okay, yeah?
Yeah.
Right, so we'll leave this exercise then as your homework for this one then.
Oh, we're not doing the other question.
No, they're both the same, so one is enough. Yeah. So if you can do this one as the homework then, the regular homework, it's on Moodle. It's on Moodle. You want to take a picture of it? Yeah. Anyone else need to take a picture? No, I close it?